So looking at double replacement reactions, what we need to start thinking about is the word soluble and insoluble. So if something's soluble, such as salt or lemonade powder, what does that mean it will do? Well, we know that something that's soluble is going to actually dissolve. So the word insoluble or not soluble means that it will not dissolve. Well, if you're not dissolving, then you're going to stay in your original physical state. In our case, we're going to be focusing that on solids. So we're looking at double replacement reactions. We know double replacement reactions are when ionic compounds dissolved in water will typically switch partners. And by partners, I mean switch cations or possibly even switch anions, depending on the compound. We know that a double replacement reaction will occur if you make a gas, water, H2O or HOH, or a precipitate, that solid that we were talking about, something that is insoluble in water. So by using table F, we can actually predict solubility. Remember, soluble compounds are compounds that stay dissolved. So compounds that are dissolved in water, they stay aqueous, dissolved in water. Insoluble compounds, we know, are compounds that are solids, okay, also known as precipitates, and we know that they do not dissolve in water. So these insoluble compounds are the things that we need to focus on in determining if a double replacement reaction did in fact take place. So just to get some practice, let's look at table F. Looking at table F in your reference table, we know this is the solubility guidelines for aqueous solutions. So we're going to look at the following compounds, and we're going to determine if these are in fact soluble or insoluble. So by looking at those, we have some exceptions. So if you're an exception to being soluble, aqueous, okay, so in this case we're going to put AQ above here. So if I am soluble, I know I am aqueous. So if I'm an exception to being soluble, then I know that I am going to be a solid or a precipitate. If I am insoluble, then I know I'm going to be a solid. And an exception to being insoluble, we know, means that you're going to in fact be aqueous. So looking at the following, we have NaNO3. So let's look at sodium. And is there anything that we can use to identify a sodium? Well, on our insoluble or soluble compounds, you're going to see nothing about sodium, but we do see something about a nitrate, an NO3. And we know that all nitrates are actually soluble compounds. So in this case, we know that this is going to be defined as AQ, or aqueous. AgCl, if we're looking at this, we know it's going to be classified based off from the halides, and if it's an exception, which it is indeed, because it is a 1-to-1 ratio, so we know it's positive silver, so +1 to chlorine. We know we're an exception, so that means that we are going to in fact be a solid. Looking at our calcium sulfate, looking for a sulfate, see if we have anything that identifies this as a sulfate, and we don't see anything until we look down here. We see sulfates when combined with Ca2+. Well, sulfate we know has a 2- charge, so we know this must be calcium with a 2+ charge. So we know this indeed is a solid. MgSO3, or SO4 in this case. So again, we're looking at a sulfate, but we are not an exception. Therefore, we know that this indeed is going to be aqueous. Looking at Na2CO3, looking at CO3, we know we're in a carbonate. An exception to that is bonded with any group 1 ions. Sodium we know is in which group? In group 1. Therefore, we're an exception to being insoluble. Therefore, we are in fact aqueous. Next one that we have here, we have a hydroxide. So we're over here in hydroxides. And we are Ba. So Ba we know is actually an exception. So we are going to be that of aqueous. One thing I strongly encourage you to do is that when you are solving these questions here, always make sure that you know is aqueous, solid, solid, aqueous. By identifying these, you can see how quickly you can identify your products or possible compounds to be that of solid or aqueous. Next one we're going to look at here is a phosphate. Looking at a phosphate, we're over here, combined with group 1. Calcium we know is actually not a group 1, so we know this is indeed going to be that of a solid. HOH. HOH is the unfamiliar way that we talk about water, but since it is indeed water, we know the physical state of water is that of a liquid. Last one, second to last one we have here is ammonium and a hydroxide. So we can look at this in either way. So ammonium, we know all ammoniums are aqueous. If we judged it based off the hydroxide side, we know that if it's a hydroxide combined with that of ammonium, we are still in the aqueous form. So we know that this one is in fact going to be also AQ. Last one we have here is lead. Lead, Br2, so we're looking at Br2 maybe. Halides, halide with that of lead, double check our charge. Br is a minus, so we know this has to be a 2+. So we know we're an exception to being aqueous, therefore we know we are a solid. Apologize, my S's seem to appear more like 5s when using my cursor. So, next thing that we're going to look at is we're going to look at some examples on the whiteboard. We're going to look at how do we actually make these double replacements take place, and can we identify, is there an actual double replacement, or do both of our products stay in the aqueous form, not producing us a water, a gas, or that of a solid.